Hi everybody, welcome back. I'm Ben and this is Nick. We're from the Centre for Organic Electronics at the University of Newcastle, and in this video we're going to go over some data that we have collected. You would have seen us doing that in the previous videos. We have written up the formulas that we need, and we've also pre-drawn the IV curve, the current voltage curve that has the data we collected in the previous video. Now, just a point to make is that this data is from when we tested the cell under our LED solar simulator rather than the data we got outside. The data we got outside was fine, but we had a lot of cloud cover, and so the values were moving around a lot. So we decided to use the solar simulator values. And that's why this SI value, the solar input here, is 1,000 watts per meter squared, because we know that that solar simulator has an output wattage of 1,000 watts per meter squared. We also have an area here of the solar cell, so 13.5 centimeters squared. Now, another important point to note is that when we transfer this area up into this equation here, we're going to have to convert the centimeters squared into meters squared. We've got to have the units in meters squared over here. But it's more convenient to write it in centimeters squared. So to calculate our efficiency, we need a few things, but the first thing we're going to need to calculate is the fill factor. So that's this equation here. So the fill factor is Vmax times Imax over VOC times ISC. So that's the open circuit voltage times the short circuit current underneath over the maximum voltage and maximum current. So this top value here is our maximum power point. So if we look on the IV curve, you can see we've pre-drawn this point in here, and we have a Vmax value of 0.45 and an Imax value of 68. Now, the way that we found this point is we took all of the data that we had, so the voltage and the current value at each point, and we multiplied those together to give us a power. And what we're looking for is the maximum power number once they're multiplied together. So once we have that maximum power, we know that that's the maximum power point. So if now we put these numbers into the equation, so we've got this equals, I'm just gonna, so Vmax is 0.45. And it's times 68. And that is over our VOC and ISC. Now, I don't have those numbers on here, so Nick, do you want to show us where those are?
For this curve, our VOC was 0.58. Just to rewrite that.
Yeah.
And it was an ISC of 98 milliamps.
All right, so let's put those in here. 98.
Yep.
Okay. So we've got those numbers in there. Now, if we did the math, that will come out to, I believe, 0.55. Which is the fill factor we'll then transfer into the efficiency calculation. When we're talking about fill factor, though, you'll often hear people say the fill factor was 55%. So they've just converted that to a percentage, so multiplied by 100. But when we're doing the calculation, we leave it as a fraction of 1. Okay, so we now have our fill factor. Time to move on to the efficiency.
Yep. It looks like we've got everything we need now to work out the efficiency. So let's go about doing that. So what have we got here? We've got 0.58.
Yeah.
That was our VOC. Now I'm going to do the current a little bit differently. I'm going to put it in amps now, so to 0.098.
So this is another one of those conversions we have to make. So
Yep.
It's important that you've got your units all in the right form.
I'm going to put in a fill factor of 55% or 0.55. And then underneath, I'm going to use my 1000 as my solar intensity. And I'm going to use my area as 13.5. I'm going to use a little extra conversion factor to convert between centimetres squared and metres squared. So 10 to the power of -4.
So that'll get us into the metres squared.
Yes,
Great.
for the area of our solar cell.
Okay. So if we run those numbers, what do we get?
We should get something like 0.023, which we would commonly say, that's as a fraction of 1, which we would commonly call 2.3%.
Okay. So 2.3% of the energy that's coming in from the sun is being converted into electrical energy in the solar cell. So it's 2.3% efficient cell. And that's actually quite good for these printed solar cells. Obviously, compared to perhaps some of the silicon cells you might have on your roof or you've heard about previously, that number is a little bit lower. Those cells usually run around the 20% mark, so it's an order of magnitude lower. But that really talks about the amount of area that you need for the solar cell. So you would need 10 times as much area to get the same amount of energy. And that's interesting in that in certain instances, the lower efficiency isn't such a big deal where you have lots of area. So if you think about industrial buildings, for example, they have these very large flat roofs where this could easily take up the space and give you the energy that you need. And at the same time, not add a lot of weight to that roof. So it has these printed solar cells have some characteristics that lend them towards being used in places that traditional silicon solar probably would not be used. Okay, so that's how we calculate the efficiency for a printed solar cell.
Yep.
Thanks, Nick.
Thank you.